قلت بس بظبط انه لايف على اليوتيوب كمان. اوكي.
اه تمام.
احنا لايف على اليوتيوب كمان. اوكي. طيب، السلام عليكم جميعا. ان شاء الله اليوم اول مرة، يعني اول محاضرة نبداها كذا، وان شاء الله تكون خفيفة وظريفة ليكم كلكم. في قواعد يعني اوكي. Let me speak in English. Hello everyone. I would like to welcome you all to our first lecture in this series. I just wanted to emphasize some rules. You are welcome to interrupt me anytime. Okay, this is not like a formal presentation. It's a lecture. It's open. We're open for discussions. Everyone is welcome to participate and so on. Ali, I think Dr. Ali and Dr. Mahmoud, they will help me to moderate the session and stop me when I need to go back and I mean maybe repeat something or explain it more and so on. So let me start by a simple presentation. Okay. Okay, so this is an introduction to radiation physics. Just a few slides before we tackle the topic we want to deal with. So ionizing radiation, I assume most of you are, or maybe all of you are medical physicists. So the study and use of ionizing radiation started with three important discoveries. X-rays were discovered in 1895 by William Röntgen. And then this was followed by the discovery of radioactivity by Henry Becquerel in 1896. And then radium by Pierre and Marie Curie was discovered in 1898. So since this discovery, ionizing radiation has played an important role in physical sciences. So for example, we see new sciences in physics, for example, study of atom or atomic and nuclear physics, as well as in nuclear engineering. Now we know there are nuclear reactors widely spread in the world, where we're transforming nuclear energy into electricity and so on. But most importantly for us, this discovery played an important role in medical sciences, especially in radiology, as well as in radiotherapy. So the potential benefit of X-ray use in medicine for imaging and treatment of cancer was recognized within a few weeks of the discovery of X-rays by Röntgen. Many believe this is an image of Röntgen's wife, although there is a debate on this issue. So I really cannot confirm this is her hand or not. So after the discovery of ionizing radiation, two new medical specialties, radiology and radiotherapy, evolved rapidly. Both specialties rely heavily on physicists for routine use of radiation, as well as for development of new techniques and equipment. Initially, most technological advances in medical use of ionizing radiation were related to improvement in efficiency of X-rays. In X-ray beam delivery. So in the LINAC, we started with ortho voltage machines. The dose rates were a bit low, and then cobalt sources, and then a linear accelerator. So we want, it takes a lot of energy or a lot of power to produce, to accelerate the electrons. So we want to convert, to have an efficient way of producing X-rays from these electrons. So we have to think of a target, which target should we use, and so on. Development of analog imaging techniques. So this is like a radiological or the films, that probably you haven't seen any of these, but in the past they were using films. Optimization of image quality with concurrent minimization of delivered dose. This is, I believe, an important role for a medical physicist working in diagnostic radiology, where they want The goal is, okay, we want to produce the best image with the minimum possible dose. And in radiotherapy, of course, the interest in the past was, let's try to find higher energies, let's develop beams with more penetrating power, and so on. So nowadays, most developments in radiation medicine today are related to integration of computers and imaging. Now, we're in the digital world. We have these digital detectors. We no longer use films for imaging. So, okay, these detectors, they need to, a lot of advantages. First, the images in a digital format. But we really need to investigate the type of more efficient detectors, more detectors with high resolution, and so on. Development of digital diagnostic imaging techniques, incorporation of computers into therapeutic delivery. I don't know if there are any, at least in this region or in the Middle East, any radiotherapy. Their Linux are not really controlled by a computer system. Radiation dosimetry, so improved in theoretical algorithms and introduction of Monte Carlo techniques in the determination of dose distributions in radiotherapy. This is a very important issue for us in radiotherapy, where we are physicists. When we do our measurements, we usually do them in water, and we use treatment planning systems today, computers with algorithms that will take into account heterogeneities to correct the doses and the distribution based on the real heterogeneity of the patient. However, these algorithms, they developed gradually. They started with pencil beam algorithms, then we went for convolutional CCC algorithms, and nowadays Monte Carlo techniques might have a role actually in the future in treatment planning. So we need to understand the physics, how we use Monte Carlo, how to develop these Monte Carlo codes. We need to understand how radiation interacts and so on. So that's a very important thing. So all of today's advancements would not be possible without understanding of physics of radiation. That's the bottom line, okay? Many of us work in clinics. Definitely we know how to do measurements, we know how to calibrate things and so on. I believe we are still physicists, and we cannot function without really a good understanding of physics of radiation. So questions to think about. So production of X-rays. In KV X-ray equipment, the initial electron beam direction is perpendicular to the desired X-ray beam. So this is a typical X-ray tube. We have an electron beam generated from the cathode, and then we have the anode. So the question is, why do we have the orientation or of the X-ray tube in such a way? Why do we put the patient here? Why don't we put the patient here? Why is it perpendicular? In contrast, when we're dealing with linear accelerators in MV Linacs, so we have an electron, and the electron is, it's in the direction of the patient. The patient is somewhere down here. So why do we put the target such that it's in the direction, so the electron beam is in the direction of the patient? So you see the difference between the two? Here, electron beam is perpendicular to the patient. So the patient is in direction, the electron beam is in this direction, whereas in a linear accelerator, we have the patient down here, and then the electron beam is, it's in the same, or shooting towards the patient, and this is where we put our target to generate X-rays. Conventional X-ray imaging units have tungsten targets. Okay, that's why do we use tungsten, for example? That's a question. Okay, is there physics that dictates this, or is just something else? Conventional mammography units use molybdenum or rhodium targets. Why don't we use, although I believe nowadays modern mammography X-ray units, they do actually have tungsten targets. But mammography, usually they will have molybdenum and rhodium targets. Why is this the case? Okay, modern digital mammography units are reverting back to this is what I mentioned, that in the past they were using molybdenum and rhodium instead of tungsten. But nowadays we're using tungsten back again. I think because we have detectors we have. Okay, so choice of X-ray, KVP. Okay, when we want to do an image, okay, low KVP setting is used to image a bone, for example. But in radiology, we would use, for example, a high KVP setting, about 100. This is probably around the 50, 60, 70, maybe KVP. I'm not a diagnostic physicist, so I don't know exact, but I know it's in that range. But when we want to image the lung, so this is not a CT, this is just a regular CT, a regular projection image. So we would not actually use a low KVP. We will use actually a higher KVP, around 120 KVP. We use this to image the chest. Why is this? Okay. So in order to start, inshallah, this course, we will address some of these questions. And we start with the physics. So let's start with the basics. So physical quantities are characterized by their numerical value, magnitude, and associated unit. Okay, for example, mass, 21 kilogram, energy, 6 MeV. So usually my students, when they come and say, and I ask them, okay, what's the energy of the beam? Or whatever, a quantity that needs a unit. Usually they will give me the number, but without the unit. So this is an issue. We as physicists, we really need to be careful about this, okay? So a mass could be in pounds, could be in kilograms, could be in another unit. So we need to be specific when we describe the physical quantities. We have to remember that they have a magnitude and there is a unit for these units. So the currently used metric system
دكتور عميد
نعم
بعد اذنك سؤال هنا في السلايد اللي فاتت. دلوقتي نفرق ازاي بين لما نيجي نقول انرجي بين الالكترون والفوتون في الجزئيه
دي حاجه ثانيه اوكي اوكي لانه احنا okay when we're talking about just okay since you triggered this question okay when we say MV okay or like for example when we state for example KV peak in diagnostic KV peak okay or MV this means it's a spectrum. So when we say a 6 MV beam this means that the photons that are coming out from the LINAC they will have different energies, a range of energies ranging from 0, from minimum, and maximum of 6 MeV. So the maximum possible energy of a photon is going to be 6 MeV. But since it's a spectrum, we call that beam a 6 MeV beam. Okay. Now for electron beams in the LINAC, the electrons coming out from the LINAC, they are very close. They're almost monoenergetic. So that's why we call them 6 MeV, okay, for electron beams, because the electrons that are coming out from the LINAC, they're monoenergetic. All of these electrons will have an energy almost 6 MeV. That's why we call this beam 6 MeV beam. But in a photon beam coming out from a LINAC, we will call it a 6 MeV beam. Now, by contrast, when we describe cobalt beams, cobalt are monoenergetic, or we can regard them as monoenergetic. So you will find a lot of the time they will call the cobalt, the beam coming out from a cobalt unit to be 1.25 MeV. Although there are 2 photons, but on average, you know, or you know, it's just like almost like a monoenergetic beam. So for cobalt, for example, you will see that they will put energy of 1.2 MeV because it's not a spectrum, a true spectrum like LINAC. Okay.
اوكي تمام.
Any other thing?
هو that's just because sometimes in literature they asking to write in MEV even for photon.
Where is that?
In literature, some literature write it even for photon, write it MEV, and say because MEV is not energy unit. So
no, when you're talking
debate.
when you're talking about an energy, okay, of let's say a beam coming out from a linear accelerator. So usually we will use the average energy of the beam. That's the right way to do it. So we say, okay, roughly it's about 1/3 of the maximum energy. So the beam coming out, the photons will have an average energy roughly around 2 MeV. That doesn't mean all the photons are coming with 2 MeV, but
Yeah.
the spectrum. But the convention is when we write 6 MV, it's basically a spectrum. It's not a unit. So it's not a unit. It's not a unit of energy in this case. It's more like a descriptive thing for the beam that comes out. Okay. For example, like here, when we say in diagnostic, when they put a KV peak, this is actually the peak potential, because sometimes the potential could be the potential is not constant in an X-ray tube. Okay, so the potential fluctuates. So the peak potential is 80, but because it's like it follows like a sine wave. So the potential difference between the in an X-ray tube is not really constant. It's not fixed, but it oscillates or fluctuates. And the way we describe the beam that comes out from such unit is we select the maximum photon energy, and that maximum photon energy is related to the peak potential of the X-ray tube. So the beam is then we say, okay, it's 50 kV peak or so. Okay, so the currently used metric system of units is known as the it's the International System of Units, or SI units. That's what most of the world, I think, use, except 3 countries. I think the States, Myanmar, and I don't know, maybe another country in Africa. They don't use the metric systems. So in the SI unit system, there are base units for 7 physical quantities. These are listed. So we have length. The unit for length is meter, mass, kilogram, time, seconds. Electric current is ampere. Temperature, Kelvin. And amount of substance is the mole. And luminous intensity is the candela. So these are the base units, 7 base units in the SI system. Now, any other quantities, these are called derived quantities. These are derived in terms of the 7 base quantities via a system of quantity equations. For example, when we talk about the velocity, we know the velocity is basically the distance divided by time. So the unit for the velocity is then meters per second, okay, and so on. Then in some situations, we might actually replace these derived units with a special unit. Give you an example, is the Newton. So the Newton is the unit for the force, but force equals to ma. So basically, the force equals to the mass times the acceleration, which has a unit of, in the SI system, based on the base units, it's kilograms meters per second squared. But then, in honor of Newton, okay, we're going to call this quantity kilogram meter per second squared to be equal to 1 Newton. We have other examples. For example, in the becquerel. The becquerel is the actual unit is per second, okay, the disintegration per second, but we give that quantity a special name, which is the becquerel. Okay. So the SI derived units for these derived quantities are obtained from these equations, and okay. We also have, so these are examples. We have the area, meter squared, speed, mass, density, okay, kilograms per meter cube, force, energy, and electric charge is a derived unit because the ampere is the base unit. So the electric charge is basically the current multiplied by time. And we also have the SI uses prefixes to form decimal multiples. So all of this is, I think all of you know these things. For example, when you say centimeter, millimeter, micrometer, what do they mean? Okay, kilometer, for example, kilo. So these are the prefixes used. So this is just a table, Forces in nature. There are 4 forces in nature. We have the strong force. This actually is the force that works It's an attractive force between nucleons, so between protons, neutrons, proton, proton, a neutron, neutron. So there is a strong force between these nucleons. And if we and that force has a very short range. So the range is about 10 to the power minus 15 meters. So this is if we call it a Fermi, or if we look back, so 10 to the power minus 15 is a femto. So we can say it's about a femtometer. That's the range of the strong source. So if the two particles are at a distance more than 10 to the power or 1 femtometer, then the strong force is going to be negligible or zero, actually. And then comes the electromagnetic force. So this is forces between charges. So it has a relative strength of 1/137 compared to the strong force. Okay, so it's a bit weaker. It's about 100 times weaker than the strong force, but its range is up to infinity. Then we have the weak force. No one should ask me about particle physics. I'm really not good at that. Okay. But the relative force is really very small compared to the strong. And also it has a short range, even shorter than the strong force. And then we have the gravitational force, which is much, much weaker than the strong force, but its range is has a range of infinity. Fundamental physical constants. So we know the speed of light, 3 times 10 to the power 8 meters per second. We have Planck's constant, and we have the electron charge. Okay. These are just a list of some of the particles that we're familiar with. So a photon, the charge of a photon, the mass of a photon, and the relative mass energy. I hope all of you now know this equation, the famous equation of how to convert mass into a rest mass energy equivalent. Okay, and we have the electron, positron. The charges, they have the same charge. Sorry, they have the same mass and they have the same charge, but they have opposite charges. And the rest mass for both particles is 0.511 MeV. We have the proton. The proton has positive 1 charge, 1 E, but it's much more massive than an electron and a positron. It's almost about 200 times more massive. Sorry, 2,000 times more massive than an electron. Okay, so if you 2,000 times. So this is the rest mass energy of an electron. For a proton, it's almost like 1,000. Imagine 1,000 divided by 0.5. This is roughly around 2,000 times. A neutron doesn't have a charge, and it's a little bit more massive than a proton. Almost the same, but it has a little bit more mass. And then we have the famous alpha particle, which has a charge of +2. And it's more massive than it has, we now know it has actually 2 protons and 2 neutrons. So it's about 4 times more than the mass of these of the proton and or a neutron. Okay. Can someone tell me why this is not just 2 times the proton mass plus 2 times the neutron mass? If you multiply 2 times this plus 2, because an alpha particle has 2 protons and 2 neutrons. So why isn't the mass of an alpha particle equal to the mass of 2 protons plus 2 neutrons? Anyone can tell me that?
Hi, it's due to the strong force energy matter conversion.
Yes. So we need some of that energy is actually converted into binding energy. So to bring these protons together and the neutrons, keep them together, we need to convert, or these particles will lose some of their energy, and that energy will become binding energy. Another example is, for example, if you take a nucleus of carbon. So carbon has 6 protons and 6 neutrons. So carbon 12, we're talking about carbon 12. If you weigh a nucleus of carbon, you will find the weight or the mass energy of this particle is less than the mass of 6 protons plus 6 neutrons, because some of that mass was converted to energy in order to bind. So the atomic structure, acceptable atomic model. Today, the acceptable atomic model is actually proposed by Ernest Rutherford and Niels Bohr. These are the ones who are credited for developing what we believe how an acceptable model for an atom. I don't believe anyone has seen actually how the atom looks like, but this is the model, and today we're going to see one experiment. Why do you want to control my screen, Ibrahim? Okay. Okay.
I am sorry. غصب عني معلش.
Right. So this model, basically we have a positive small nucleus, and in the middle here has a size of about a femtometer or maybe 10 femtometers. That's the order of magnitude of the size of a nucleus. And there is this famous equation approximates where we can actually approximately calculate the radius of a nucleus, which is, I believe, 1.25 Fermi times the atomic mass, the power 1/3, something like this. And then we have electrons in planetary orbits. And the nucleus has a size of about 10 femtometers. And then the atom itself has a size of an angstrom, roughly. And the constituents of particles forming an atom, we have protons, neutrons, electrons, and protons and neutrons are known as nucleons and form the nucleus. These are also some basic definitions. Atomic number Z, that's the number of protons and the number of electrons in an atom. Okay, atomic mass number. So this is the number of nucleons, that's the number of protons and the number of neutrons in an atom. And the number of neutrons in an atom, and which is basically the atomic mass number minus Z. We can put it like this. So the atomic mass is expressed in atomic mass units. Okay, so now we want to talk about the mass of an atom. It's expressed with an atomic mass unit. We could express it in SI units, but it's not practical. If we look back, the masses of where is someone is writing on my okay. So if we look at the mass of an electron, mass of a positron, and so on, expressed in SI units, these numbers are really difficult to memorize, okay, and not practical actually to use. These are more actually easier to use. So we express this in terms of an atomic mass unit. So it's not just on the mass itself, but also we define the mass energy equivalent of a carbon-12 to equal to 1 atomic mass unit. So 1 atomic mass unit, it's 1/12 of that. It actually went through history. So initially they started saying, okay, simplest atom is hydrogen. Let's call the mass of a hydrogen is 1 atomic mass unit. So if we had helium, for example, they would say roughly it's about 4 atomic mass units, plus or minus, okay, and so on. And then they moved to oxygen. They said maybe we should not use hydrogen. We're going to use oxygen. So oxygen 16 was actually the basis for defining the atomic mass unit. So atomic mass unit was then defined as the mass of 1/16 of the mass of an oxygen 16. But today, they reverted to carbon. So the 1 atomic mass unit is equal to 1/12, the mass of a carbon atom, okay? And this, if we take the mass of carbon, convert it into energy equivalent, and then divide by 12, you will find that 1 atomic mass unit is equal to 931.5 MeV per centimeter, okay? So we're dividing by C squared. So we're dividing by C squared because we're talking about a mass, not mass energy equivalent. Okay, this is always a mistake I make. Like whenever we say a mass of a particle, we should write so a mass of, for example, electron is going to equal to 0.511 MeV per c square. Okay, but the mass energy has a unit of MeV. So the atomic mass, like one of you said, the atomic mass is smaller than the sum of the individual masses of constituent particles because of the intrinsic energy associated with binding the particle nucleons with nucleus. And now if we want to define the nuclear mass, so it's very simple. We take the atomic mass and let's remove, these electrons. We want the mass of a electron. Okay. Notation, we know these notations, how nuclear physics, the convention, how a nucleus is, so we write the symbol of a nucleus and then Z as a subscript in front of it that represents the atomic number, and then a superscript A as the atomic mass number. Okay, this is something will come handy as we move on, is that the protons to nucleons ratio. Okay, so roughly in an atom, we will find that the number of protons roughly is equal to half the number of nucleons. So for example, we have carbon 12. Carbon 12 will have 6 protons and 6 neutrons. So Z over A in this situation is 0.5. Okay. As we increase, as we go to higher Z, this factor is going to be less, and I think it reaches around 0.4 or 0.35 for very high atomic number. So for example, if we take lead Z for lead is 82, and for example the A for lead could be 209 or something large. So we find that actually there are more neutrons than protons in a lead nucleus. And the reason is because when we're putting a lot of these positive charges inside this nucleus, so the more protons we have, then the more repulsion between them the nucleus is going to face. And in order to overcome that, we need to compensate or we need more neutrons in order so that the strong force becomes large enough to hold the nucleus together, not to be disintegrated because of the Coulomb force between the protons. So in general, at low Z materials, this ratio, the Z over A is 0.5. As we go higher, this ratio slowly decreases and reaching around 0.4 or 0.35 at very high atomic elements. The only exception to this rule is hydrogen. Hydrogen, we know it has 1 proton, no neutrons. So Z over A is 1. Okay, here because we're talking about hydrogen with the different isotopes of hydrogen, but hydrogen with 1 proton, that's the dominant or the most abundant in nature. So that's why Z over A is roughly equal to 1. This will come handy when we start to look into cross sections. Why for bone we see something, whereas for tissue it's different. Okay, or for water is a bit different. It's all related to the content of how much hydrogen is in that material. And helium-3 is also another exception. So Z over A is 0.67. Okay, so I'm going to stop here. This part we can leave it. Okay, so we're going to leave this. And we're going to move to today's subject. Okay, any questions so far? This was just a refresher to all of you. So let's. Okay. So today we said, as I mentioned earlier, that the acceptable model today for an atom is actually the model, the Rutherford Bohr model. Rutherford, he was in his model, he explained, why we have a nucleus. And then Bohr came and explained, the orbits of these electrons and so on. Okay, so I don't have a massive presentation here because I'm going to write a lot of stuff. But this is basically from the book Radiation Physics for Medical Physicists. I think chapter 2 deals with this issue with a lot of physics there. I'm just touching on the basic stuff that at least if someone understands the basic stuff, then they can go and read the chapters that has more advanced physics in it. Okay. So there was an experiment, I think in the let me get the date properly. Okay, in 1909. So there was an experiment, Rutherford, Geiger, and Marshall experiment. Basically, they wanted to study the atom. Okay, and a good way to study atoms even today is basically let's accelerate some particles, let's shoot these atoms, and let's analyze whatever comes out from that experiment. Okay, this is a scattering experiment. So even in CERN, for example, today, they have these massive accelerators. They can accelerate particles to very high energies, but it's the basic concept. They have a target, they accelerate particles, or maybe they accelerate particles from different sides, and then at the point of collision they have detectors around them, and they look what they collect what's coming out from that experiment, from that scattering experiment or collision, and then based on that they start to think, okay, how things, how does this, what could explain, for example, the outcome that we are seeing. So basically they wanted to, I really cannot talk on their behalf, why they did this experiment, but I would think that they wanted to really study, the atom itself. So they decided, okay, let's use a radon emitter, radon 222. So this radon emits alpha particles with an energy of 5.5 MeV. So they put this in a container, or it's like lead, so that only the beam, and they put only a small hole there. So then they form a pencil beam, and they put at some distance, they put a gold foil that is very thin, of the order of a micrometer. Okay, and they put all of this is actually in vacuum, because if alpha particles are going to, there is air between the source and the target, so maybe something happens, the results of their experiment could be actually due to something happening in air. So they wanted to eliminate that part, and they put all of this in vacuum. Okay, and all what they have done is very simple. Let's shoot alpha particles in the gold foil, and we have a detector. Let's see how many alpha particles we're going to collect at different scattering angles. That's the whole thing. Okay, what they've found is that 99% of the alpha particles incident were scattered at angles less than 3 degrees. So the majority of the alpha particles were scattered really at very small angles. So this is the direction of the original of the beam, and majority of the alpha particles were collected within 3 degrees from their original direction. But what they have found also is that since they moved the detector all around, okay, and they started to see, they have started to collect the alpha particles that are collected at angles greater than 90 degrees. Okay, And based on the experimental results, they found about, or based on their measurement, they found that for every 10,000 alpha particles, they're going to get one alpha particle that is scattered at an angle larger than 90 degrees. So the probability, that means the probability of an alpha particle to be scattered at an angle greater than 90 degrees. So this is the angle greater than 90 degrees. This is going to be about 10 to the power minus 4. That's the probability of 4.01%. Put it in this way. So 99% of the alpha particles within 3 degrees, but they're finding about 0.1% to be scattered at an angle more than 90 degrees. So at that time, there was an atomic model for an atom. This was proposed by Thomson. Thomson, he's the scientist who discovered the electrons. Okay, so basically he proposed that, okay, the model for an atom, we have a sphere of a diameter of 1 angstrom. This is the size of an atom. This sphere has a positive charge that is uniformly distributed within the sphere. And then within the sphere, we have electrons. So these electrons are in some rings or some locations inside this sphere. Okay, so because they knew that the atom is neutral, so the number of electrons or the charge of these negative electrons has to equal to the number of positive charge that is actually within this sphere. Okay, so these electrons are fixed at some equilibrium positions. And when they're fixed, when they're in these positions, no radiation is emitted from the atom. At that time, they could see, for example, different atoms, they emit radiation. They emit, now we know these are called characteristic X-ray or characteristic photons, but they had actually some form of radiation. Some atoms, when they are excited, they emit photons. So this is what was known. So based on his model, he said, okay, well, how to explain what happens is, okay, when atom is in excited state, what happens is one of these electrons, it actually starts to oscillate. So it will oscillate like this, okay, back and forth. And while it is oscillating, it's going to emit radiation. Okay, this is through dipole oscillation. If you use in electromagnetism, when we have a charged particle, an electron, when we have an electron that is accelerated or decelerated, okay, so when it is moving in a steady, constant velocity, okay, no radiation is emitted. But when we accelerate the electron or decelerate the electron, we get photons coming out. So it's the same principle that these electrons, when they are oscillating, there is going to be subjected to acceleration and deceleration. And when they're doing that, then they will emit, and so they will oscillate with a specific frequency that is specific to a given atom, and then they will emit these characteristic photons that is related to their oscillation. Okay, so basically the model could explain a lot of the physics, at that time. So people accepted it. So this is, okay, the mass of the atom is distributed uniformly over the volume of the atom. Negatively charged electrons are dispersed uniformly. And this model is sometimes known as the plum pudding model. So based on their model, there is some math involved in this. And basically they wanted so these Rutherford and Geiger, and they had this experiment, the alpha scattering experiment, and they wanted to calculate, okay, does Thomson model predict what we're seeing from our experiment or not? So based on the Thomson model, so let me just go back and let's do something here. So the Thomson model basically assumes that we have atoms. They are like this. So these are the atoms of the gold coin somehow. Yeah, and then we have layers of these atoms like this. Okay. So after a few layers, what happens is we have, these are our alpha particles. Okay. Then they measure, they look at the angle, okay, of these alpha particles as they come out. And they said, okay, they made some measurement to calculate what is the mean average. So they wanted to calculate what is the mean. That's based on experiment. That's the mean average scattering angle. And based on these quantities, and they came up, or they used this equation that calculates the number of so based on the equation, this is the number of particles, alpha particles, okay, scattered within a small angle d theta is given by this equation, okay? The issue, so when we integrate, so for example, if we want to get the results from the experiment, what we need to do is we do this, the following, okay? So if this is the formula, we have n of theta, d theta, equals to some function of theta, okay, d theta, okay? So if we want to get the probability of the particles that are going to be scattered at angles greater than 90, all what we need to do is then we integrate this. So it's basically n0, n theta greater than 90 degrees, okay, over the original. These are the number of alpha particles that are incident, is given by, we take this from scattering, and this is from pi over 2 up to pi. This is 90 up to 180. And then we take this thing, so basically it's n d theta. So we need to integrate this function, and we divide everything, or this divide by n0. This is the constant, so we can remove it from here. Okay, and we put over n0. Okay. So when they did this integration, and I think I have it in the book, this gives us that the probability, this factor, n of theta greater than 90 degrees over n0, this is roughly about 10 to the power minus 3500. Okay. Yes, I thought I actually had it here, but anyway, in the book, there is actually that describes this part. It's just an integration of this function. All what you need to do is to integrate this function. This thing is a constant. So theta squared with the bar here, this is the mean where this is something determined from experiments. So we need to integrate with respect to theta. This is the constant, and here, this is actually the result here. This is a constant. When you integrate this, you will find that the result is about 10 to the power minus 3,500. So the bottom line is that based on the Thomson model, yes, they have seen 99% of the atoms are actually scattered in the forward direction at very small angles. That's fine with the Thomson model. But the probability or the measurement that they are seeing for alpha particles scattered at 90 degrees, that could not be explained by the Thomson model. So it's ironic. Sometimes when I ask, you know, this when I think when I was taught in high school about the Rutherford and about this experiment, and said, yeah, you see, because of the atom, most of the atom is actually vacant. There is vacancy there, and we have, this explains actually why a lot of the alpha particles actually pass through and no scattering happen. But actually, this is not correct. Okay, it's not the forward scatter, it's not what they actually passed or these small angles. That's not the issue. The issue is the back scattered alpha particles. This Thomson model predicted a negligible probability, whereas actually the experimental results shows that, you know, although it is small, but definitely is not. So here, if we share this. So here, this is the result. So all what we have done, they have done here is just integrate that function. If you're good at math, it's very simple actually. And then they found that this is the probability. So of course they wanted to explain, you know, the model or the experiments, that the result that they're seeing in the experiment. So Rutherford, you know, came up with a different model. He said, okay, I'm going to assume that, okay, then the atom actually consists of a nucleus with a massive, with a mass that is concentrated in a very small, in the nucleus, very small volume, okay, and that nucleus is positive. At that time, they did not know we have protons, neutrons, no. So that's the assumption that we have a small nucleus with a positive charge. And the size of this nucleus is of the order of a femtometer. That's the size of the nucleus. We know for gold, for example, the size is different. It's larger than this, but that's, you know, it's of that order, okay? The bottom line is very, very small. And how do we account for the negative charge electrons? Okay, we have some electron charges, but these are, you know, rotate or orbit or revolve about the nucleus in the cloud. At that time, we did not have like energy levels and so on, just in a cloud. And, you know, this radius of this cloud is the size of an atom, which is about 1 angstrom. So now the kinematics of Rutherford. So that's the model. I said, okay, now I need to derive some physics, you know, to see, you know, does it explain the results that we're seeing or not? So the assumption is that, you know, the scattering of the alpha particles on gold is an elastic scattering event. Elastic means that the kinetic energy of the alpha particles, the incident energy is going to equal to the final energy. So after the alpha particle is scattered, its kinetic energy is going to equal to the incident energy. Okay. During the scattering process, this energy could change, you know, the velocity and so on, that's fine. But we're talking about the final and the initial, okay? The another thing is that we're going to assume, the assumption is that the mass of the gold nucleus is much larger than the mass of the alpha particle. What does this mean? It means that when we have this collision, essentially, the gold nucleus is going to be stationary. It's not going to move, okay? Because it's very massive. Imagine if you have a ball and you throw the ball on a wall, for example, or a ping pong ball. Let's look at a ping pong ball, and you have a bowling ball. Take this ping pong ball and throw it on the bowling ball. The bowling ball will hardly actually move. It's very massive. So it's the same thing here, okay? Because and the essential part about this is that this will make, I mean, we will have a conservation of energy initial and final and so on. No energy is going to be transferred to the nucleus. So that's the second assumption. The scattering of an alpha particle on atomic electrons is negligible. We have these electrons, electron cloud. So the alpha particle, while it's moving, okay, definitely it's going to interact or could hit these electrons before, interacting with the nucleus. Well, that scattering of that electrons, they do not have any effect on the alpha particles. Okay, so their effect is negligible. The reason is the mass of an electron is much smaller than the mass of an alpha particle. Nowadays, we know that the mass of an electron is 0.511 MeV per c squared, and the mass of an alpha particle is 3738 MeV per c squared. So it's about 6 or 7,000 times, more than 7,000 times more massive an alpha particle compared to an electron. The alpha particle does not penetrate the nucleus, so there is no nuclear reactions. And the classical relationship for the kinetic energy of alpha particles, we can use this. We don't need relativistic. Okay, this is valid. Okay, where the velocity of the alpha particle is much smaller than the speed of flight. Okay, and I mean, just to remind you how to calculate these things. So when we have an energy of a particle, okay, this is the kinetic energy. Okay, classical is 1/2 times the mass times the velocity squared. Okay, but relativistically, so this is the classical. Whereas relativistic, this is equal to gamma minus 1 times the mass c squared. Okay, so this is the relativistic kinetic energy, and we know gamma, this equals to 1 over the square root of 1 minus beta squared, where beta equals to the speed of light, the velocity relative to the speed of light. So all what we need to do in order to see this assessment, is it correct or not? So what we need to do is, okay, the energy, this is something they knew. The energy is the kinetic energy of the alpha particles. This is 5.5 MeV. Okay, equals to gamma minus 1, and the rest mass of the alpha particle, this is 3738, I think, MeV. Okay, so the MeVs will cancel, this divide by that, and then you will do the math, and in order to determine this beta. Okay, and you will find now. Okay, and you will find that this beta is I think less than this 5% of the speed of light. So essentially, using classical mechanics, okay, works. It's good. We can do that. Okay. فأي أسئلة? Everything is fine? Clear? Mahmoud, you don't have any questions?
لا حاليا لا تفضل.
Okay. So this is the famous graph that explains or talks about, this is scattering event. Maybe I should draw it so that people understand what's going on. Okay. So we have this massive nucleus. Right here. So in the experiment, this was gold, right? And then this is our alpha particle. It comes, it's going to move in this trajectory. Okay. So this is the initial angle. And this is going to be the scattering angle theta. Okay. So one thing we have to define, we have something called the impact parameter. So this is the impact. Imagine if we put an axis, okay, around this gold nucleus, this distance, impact parameter. Imagine.
Yeah, doctor, we don't see it. We don't see it if you
Oh,
are
okay. Sorry.
drawing something.
Sorry. Okay.
Yes.
Remind me. Sometimes I get excited to share another screen.
No problem. Sure.
Yeah. So this is okay. Let me repeat this. So we have here gold nucleus. Okay. And this is our alpha particle. Alpha particle is going to move in this trajectory. Okay. The gold has a Z, I think equals to 79 for gold. And for the alpha particles, so this is the alpha particle, Z equals to 2. Okay. And what happens is there is going to be an electrostatic force. So we'll have a force like this. Okay. So we have a force, Coulomb force between alpha particle and the nucleus. So as the alpha particle, when it's at infinity, no problem. As it approaches, this force is going to somehow push away this alpha particle, and the trajectory of the alpha particle will look like this. Okay? We move in that direction. And this is the scattering angle. Okay? So one parameter we need to define is this impact. We call it the impact parameter. It's basically the distance. Imagine if we had the alpha particle, it's moving, and this is the original direction where it, if this wasn't there, the alpha particle will move along this line. Okay. So the distance between this line and the gold nucleus, the minimum distance, this is called the impact parameter of this scattering. Okay. So this shows that an alpha particle, based on the distance of this impact parameter, it will move on different trajectories. So the scattering angle will definitely depend on this impact.
السلام عليكم. معلش يا دكتور عميد،
نعم.
الصوت بس يعني بعد شويه.
طيب. This is just to show that the trajectories of the alpha particle for different impact parameters. If the impact parameter is large, okay, then okay, the force between the alpha particle and the atom is going to be weak, and then we're going to see minimum deflection. But if the impact parameter is small, then the alpha particle as it approaches, the force now is going to be large, and we can get a large deflection. So here in this line, this is a 90-degree, or even in some situations, we can get a deflection of theta more than 90 degrees. Okay, so this is the impact parameter. What will happen if this impact parameter equals to 0? This quantity is known as the distance of maximum approach. This is basically what will happen is that this alpha particle is going to move. It's like a head-on collision, but as it moves towards the target, the Coulomb force is going to slow it down until it reaches, the maximum distance, or the maximum distance of approach between the target and the alpha particle when it stops. After that, okay, the alpha particle is going to go back and move back in the same line. So this is called the distance of closest approach. Okay. So the distance of closest approach is basically, so this is when the impact parameter equals to 0. Okay. So what's the value of this distance of closest approach? Well, the problem is like we have an particle shooting like this, stopping, moving, okay, like here, and back. And here we have our gold nucleus. We can use our basic knowledge of electromagnetism, where we know that the alpha particle, when it's very far, the energy that it has is kinetic energy. But as it moves toward the nucleus, closer to the nucleus, this kinetic energy is part of it is going to move to potential energy. And as it approaches more and more, the potential energy is going to increase, and the kinetic energy is going to decrease until we reach a point where all of its initial kinetic energy is converted to a potential energy. And this will be at this distance of closest approach. This distance is the alpha n. Okay? So let's calculate this. Distance of closest approach. Basically, this is the kinetic energy of the alpha particle equals 1/2 mv squared, and the potential energy, okay, potential equals to, in this case, is going to be square over 4. We know this from electromagnetism, okay? Small z, capital Z, divided by R, okay? The total, the sum of the two, has to be constant. So initially, when the alpha particle is very far at infinity, so this is essentially, we have kinetic energy, and this potential energy is 0. When R equals to infinity, this is 0. Okay, and this equals to, or this is the initial kinetic energy, equals to 1/2 mv initial. So in our case, for the alpha particles for Rutherford scattering, this equals to 5.5 MeV. What happens at this point here? At this point, the kinetic energy is converted to potential energy. So the kinetic energy at this point here is 0. So the energy, potential energy, at distance of closest approach equals to E squared over 4 pi epsilon 0 z squared over this distance. So then it's just mathematics, how we can calculate the distance of closest approach if we know the kinetic energy. We can write this in a better form. So let me delete this. So the distance of closest approach equals to E squared over 4 pi epsilon 0 times Z, this for the alpha and this for the goal, divided by the energy. And energy. Just want to look at my notes. Yes. Now we can evaluate this, but I'm going to show you some tricks. Okay, this constant, we have some nice constants that probably we need to know. H bar C, so Planck's constant. So H bar is Planck's constant divided by 2 pi. This equals to 197.2 MeV Fermis or femtometers. Okay, and we have this quantity E squared over 4 pi epsilon 0 divided by 1 over H bar C. This equals to 1 over 137. Okay, has no units. So we can use these two formulas in order to make this in a nice, write it in a nice way. So we have the D, then alpha M equals to, so we need here an H bar C, so we can put here 1 over H bar C multiplied by H bar C. Okay, this is then our 1 over 37. This is, by the way, it's called the fine structure constant. It has a symbol of alpha. I don't want to use it because alpha now is our particle, 1/37, and then the h bar c. This is 197.2 MeV Fermis. Okay, divided by this.
معلش يا دكتور عميد، في بس كومنت من حد بيقول هي distance square I think. انا مش متاكد هو بيقصد ايه.
لا we're talking about the potential, we're not talking about the force. And he's right if we're talking about the force, but now we're talking about the potential. Clear or not clear؟ الشخص ده لو يطلع عشان نوضح اوكي، احنا بنتكلم على البوتنشال اللي هو potential energy. Okay, we're not talking about the Coulomb force. Okay, so here is MeV Fermis. Okay, the reason why I like to write it this way, because our energies are all in MeVs. Okay, if I'm going to use this E squared over 4 pi epsilon 0, I have to, the Coulomb 1.602 10 to the minus 19. It's correct. It's going to be correct. I'm not saying it's wrong. But now when we write the formula in such a way, so this is a constant here. All of this is constant. So I just 197 divided by this, and we get energy. So the energy, so in our Rutherford scattering, this energy, this was 5.5 MeV. Okay. So let's plug this value. So I don't have a calculator, and I think you will get 41. If I'm not mistaken, we're going to get 41. Yes. So, okay, there are two things missing here. We're missing the Z. This is for the alpha. So these two Z and the Z for the gold. So Z for alpha, this is 2, and Z for gold is 79. So if we plug these numbers for the Rutherford scattering, then we will get at the end d alpha n equals to, I think, 41.37 Fermis. Okay, or femtometers. Okay. Now remember that formula for the radius, okay, of a nucleus. This roughly given by 1.25 femtometers multiply A to the power 1 over the third cube. Okay, so A is, I think, for gold, this is 197. Okay, and if you plug in the values for this, you will find that the radius of gold is much smaller than the distance of closest. So remember in the postulates, we said that when Rutherford scattering, he assumed that this alpha particle is not going to penetrate the nucleus, is not going to reach the nucleus. Well, here, based on this part, the energy of the alpha particle, this is the maximum distance that this alpha particle can actually approach the nucleus, distance of 41.37. But the radius of the nucleus is much smaller than that. It's about, I think I did not calculate it, but this is the formula, okay, for it. And it's going to be, so the alpha particle does not actually reach the nucleus. It's not going to penetrate the nucleus. So Rutherford, in some aspect, he was lucky that the energy of the alpha, imagine they used a different source where the energy actually it's much higher than this, and it can actually reach the nucleus. Maybe they will get different results from what they're seeing. So anyway, this is just some of the things. So this is the delta, the distance of closest approach. The next thing we need to determine is, okay, what is then the relation between this speed and this scattering angle? Is there a relationship between the two or not? Okay, and if I knew what is the impact parameter? So impact parameter, scattering angle is 180. It's backscatter. When impact parameter is 0. But now if this beam is not 0, can we determine this scattering angle? Yes, we can do. We can actually determine this. And I won't go through the derivation because maybe people will find this boring unless you want to. But basically, it starts by, okay, let's calculate the change in momentum. This particle has a momentum like this. Initially, it has a momentum in this direction. And now it's deflected in this direction. Okay, so we can, the momentum was, this is the initial momentum. And this is the final momentum. And this is the change in momentum, delta P. Okay. So this is by how much it changed. Of course, since it's an elastic collision, the initial momentum and final momentum are equal to one another. So we can get a relationship between the initial momentum and the final and the change in momentum. Okay, if we look at this, the scattering angle theta, and you do this, so sine over 2. So this is now a right angle triangle, right? So let's look at this part, this triangle. Okay. So we have the sine of theta over 2. It's this angle, theta over 2, equals to delta P divided by initial P. Okay. So this is a simple relationship. But we also can calculate the momentum based on the Coulomb force. So this also could be calculated like this, as the force, the Coulomb force impact, dt. Okay, and for that person who said, you know, it's r squared, the force is e squared over 4 pi epsilon 0 z, capital Z, divided by r squared. That's the distance. That's the force. Okay, it has r squared. So what happens is that for every angle, as this particle approaches or moves towards the gold nucleus, what happens is the force, the Coulomb force, is going to increase, and actually it will be in this direction here. That's the force. Okay, the force is going to be this. So all what we need to do is, as a function of time, we need to integrate this force in the direction. This is the vector of force. Okay, and from minus infinity to infinity. So of course, this is a bit. So what we do is then we change this. We say, okay, scattering angle. We can look at this thing. Let's put this like this. Okay, so if this is theta, okay, then we can have this angle, we call it phi, and this angle phi. So as the particle approaches, the phi will have at a certain distance, it will decrease, and then it will increase like this. Okay, so the phi at here, this equals to minus pi minus theta over 2. Okay, if this is 0, this is minus pi minus 2. Imagine this is pi, just so that everyone understands what's happening. This is okay, this angle is pi, okay, 180. Now we have theta, particle went in this direction, okay. So this is it's centered between the two. So this will go from minus pi minus pi minus theta divided by 2. It's half of this angle. I mean, from here to here, this is just pi minus theta. So this is half of it, and on this side, half of it. This is just changing the limits of the integral, and then we have the force, Coulomb force. Also, we want to take the full Coulomb force. Also, we need to take the component of the force that is going to change the momentum, and this is the cosine of phi, and then we put this with respect to time. So there are some change of variables and then assumption of angular momentum is conserved, and so on. But at the bottom line, so basically we're calculating delta P from here, and we are also calculating it, we're getting it from this equation here. So that once we relate the two, let me just put the results for you. So we have delta P equals to, so this is from the integral. Okay, this is E squared over 4 pi epsilon 0. And then we have Z. Sorry, here we don't need this. Capital Z divided by, it's divided by the energy, divided by the initial velocity, and the impact parameter times cosine of theta over 2. Okay, just one has to do the math, and you will get from that first equation, we're going to get this. This is the initial velocity. Okay, so it's the initial velocity. We can put the mass and 1 over 2. And so we can change this somehow so that we reflects the energy. And then from the other equation, we have delta P equals to 2 initial momentum. Okay, so initial momentum, we can replace this because this is the mass of the alpha particle, okay, times initial velocity multiplied by sine theta. So based on this and that, we will get at the end, we will get this relationship. So here we have the B. So when this equals to that, you will do the math. So at the end, the B will then equals to this distance of closest approach divided by 2 multiplied by cotangent of theta over 2. Okay, so this relationship tells me, okay, if we have B, then we can calculate what is the scattering angle, or vice versa. So each impact parameter has its own, a scattering angle of the alpha particle. The last thing we're going to do is, okay, let's calculate. This is an interesting problem. So before I go into the Rutherford differential cross section, so let's look at this result and see, for example, can we start to think? Can we predict? Does this model then predict the outcomes of the scattering experiment? Remember what we said is that if theta is greater than 90 degrees, then the probability of being scattered at that angle is going to be 10 to the power minus 4. That's the probability. All what we have here is just a relation between B and theta. Okay. Cotangent theta over 2. Now, based on our model, so let's understand something. Based on our model, let's put it. So let's see. Again, this is B. And the particles in this. An alpha particle is scattered at a distance smaller than this B, for example, it will be deflected at a greater angle. In other words, if I have an alpha particle moving with a smaller B, then the deflection is actually going to be more. Theta is going to be more. So this gives us, a very good geometry to start to calculate this probability, meaning that if the alpha particle is then going to be incident, suppose we can calculate B such that theta is 90 degrees. So we have determined, based on this equation, what's the impact parameter. We can just plug it here. So cotangent of theta. So, okay, this is 90, 55. This is going to equal to 1. So B at for theta equals to 90 degrees. We will get this impact parameter B equals to B n over 2. I hope I have this right. Okay, because cotangent, this is now 45 degrees. So I think, yes, this is correct. What does this mean is that particles, alpha particles, that are going to be scattered, are going to be incident on the nucleus with a distance impact parameter equals to this, they will be scattered at 90 degrees. How about particles that are going to be incident with an impact parameter that is smaller than this? They will be scattered at an angle greater than 90 degrees. Okay, so this gives us, okay, this area then is a cross section. Okay, is a total cross section for.
Sorry, Dr. Wamir, mungkin
Yes.
the last point.
Okay. And we can calculate the cross section and then integrate the cross section from theta equals to 90 up to 180. I just want you to visualize this to see it in a correct way. Let's calculate the impact, because now what we're interested to do, we want to calculate what is the probability that an alpha particle is going to be scattered at angles greater than 90 degrees based on Rutherford model. That's what we want to do. And if this is not equal to the experimental data, then what's the point of this model? It's useless. Math is nice and so on, but it does not, you know, agree with the experimental results. So what we're going to do, we're going to say, okay, this is the relationship between the impact parameter and the scattering angle. If the scattering angle is 90 degrees, then the impact parameter is going to equal to, okay? This is basically, this is the impact parameter. Particles, alpha particles that are going to incident with this impact parameter, they will be scattered at 90 degrees. Theta is going to equal to 90. So my point to you is what happens if the particle, alpha particle, when it's incident alpha particle has a smaller b than this here. What's the trajectory of this alpha particle? Well, this alpha particle, a smaller impact parameter, it's going to actually be scattered with a larger theta. Okay? So if b impact parameter equals to n over 2, the alpha particle is going to be scattered at 90 degrees. If the impact parameter is smaller than d alpha n over 2, the alpha particle is going to be scattered at an angle greater than 90 degrees. And if the impact parameter is larger than d alpha over 2, alpha n over 2, it's going to be scattered at a shallower angle, okay, less than 90 degrees. Okay, makes sense? Makes sense or not? هذا الشيء.
يا دكتور وظيم معلش صوتك قطع النت.
Okay. إذا إحنا حسبنا, if we calculated an impact parameter for angles for scattering to be at 90 degrees, then if the impact parameter is less than that value, the alpha particle is going to be scattered at an angle greater than 90 degrees. That's what I'm saying. But this is now a cross section. Imagine this is the target. This is a cross section. So if an alpha particle is going to hit this disk, going to land on this disk, this alpha particle is definitely going to be scattered at an angle greater than 90 degrees. So this is the cross section, okay, of this interaction of alpha particle being scattered at angle greater than 90 degrees. Okay, so let's draw something. This is now our foil, our gold foil. And we have here, these are the gold nuclei. Okay? They are within this gold foil. Now, for each nuclei, we can draw a circle. Such that this impact parameter equals to B, so B at 90, theta greater than 90, this equals to D alpha. So the area of this disk, this area is just equals to this area equals to 5D squared. Okay? So imagine each nucleus, we have an area, this area. If the alpha particle falls within that area, it's going to be scattered at an angle greater than 90 degrees. So if we want to calculate the probability of the scattering of the Rutherford scattering experiment, well, what you need to do is, okay, let's look at this area, the areas of each individual nuclei, compared to the area of the beam. So this is the area of the beam. Okay, let's call this surface S. So we have an alpha particle is hitting on this surface. Some of these alpha particles are going to hit these small targets close to the alpha particle, the gold nucleus. If they do hit this disks, okay, or these small targets, these alpha particles, they're going to be deflected at an angle greater than 90 degrees. So to calculate the probability, all what we need to do is, okay, let's calculate the total area. We need to know how many gold nucleus are there, sum them up, and we divide this by the total area of the beam. Make sense?
Yes, it does, Doctor.
Come on.
Makes sense. Yeah.
Okay. So what we're going to do is, all what we need to do is now to calculate how many targets do we have. So this has a thickness, okay, based on the experiment. This had a thickness x equals to 10 to the power minus 6 meters. Okay. So the volume, we're going to calculate this, the volume of this foil. Of course, we have to think of just the area of the beam, not the full area of the foil, because we are interested in the scattering process. So imagine this S represents only the area at which the alpha particle beam is incident on. So the volume in that area equals to S multiplied by this X, this distance X. Okay? So the next step is, what's the mass of gold there? Mass of gold, this gold foil. Okay, again, we're talking about the mass within this volume, the beam surface and the thickness. This equals to the density of gold multiplied by the volume, which is multiplied by S multiplied by X. The last thing is, okay, how many gold nucleus are there? So if we know the mass, so the number of gold nucleus equals to this mass divided by A multiplied by an Avogadro. Okay, so think about it like this. If we had n Avogadro gold atoms, their mass is going to equal to this atomic mass, 197 grams. So if we have less mass than that, okay, that will give me, so the fraction or you know, the number of gold nucleus or the number of targets, we can think of it in this way. Of course, we have to also make some assumptions. Since the gold foil is thin, we're going to assume that, okay, there are no like overlaying of let's say a gold nucleus, and behind it is another gold nucleus. We're not going to assume that. We're going to assume that, okay, these are quite spread out because we have a very thin gold foil. Okay, so let's remove this X عشان ما تحصل مشكلة. Okay, so then the number, this is the number of, this equals to the mass of gold, which is the, sorry, the density. It's the density multiplied by the surface area multiplied by this thickness X divided by A, which is 197 multiplied by n Avogadro. So the total area, so let's, I don't know what to call it, this area where we're going to make the what should we call it? AT target. This is the area of we call this area of nucleus. Okay, and this is the area of the target. So the total area, this is basically a target equals to pi or we can write it like this, the A of a single n, okay, multiplied by this, the number of targets, number of gold, okay. Who's writing on my screen? Okay, and this equals to pi b squared multiplied by rho s x n a divided by this A. Okay. So this is the area of the target. So what we said, what's the probability then? It's very simple. It's this AT divided by the surface area. So this is the probability then of being scattered theta greater than 90 degrees equals to AT divided by S. And this equals to pi b squared times the density times S times the thickness and Avogadro divided by A. Okay. So now if we plug in the numbers, D is basically D alpha and over 2. This we said it's 41 Fermis, right? So we calculated this in the, so we can, let's delete this. So we have D alpha, and this is 41.3 centimeters, okay? And then we have, so B equals to that over 2, and the density of, I think this is 19 grams per centimeter cube. It's the density of gold. And we S, sorry, we don't need, this is not there. S plus واحد. Okay. And A for gold, this is 197. Okay, and we have X, which is 10 to the power minus 6 meters. And we have N Avogadro, this is 6.022 times 10 to the power 23 atoms per mole. Okay. So if you put, I like always put everything in terms of units, you will find that the mole will cancel, the units will be okay, will cancel out. And I did this for, so then from here we get the probability of theta 90 degrees. This equals to 3 times 10 to the power minus 4. Okay. So remember we said in the experiment, the probability of the alpha particles being scattered at angles greater than 90, this is what they found. They found it to be greater than 10 to the power minus, it's about 0.0, 10 to the power minus 4. And based on Rutherford scattering, we're getting a probability that, you know, is very close to at least it's better than the Thomson model, 10 to the power minus 3,500. This is very close. Okay. So that's no, this model, of course, there are some problems with it also. I mean, we have to be fair. Okay. Classical thing and so on. Because remember, the model assumed, for example, that the nucleus is like a point. It's very, very small. Okay, positive charge concentrated there. And we could use this potential and so on. Another thing assumed by the model is that as the alpha particle, the model assumes electrons do not exist. But in reality, imagine if the alpha particle is far from the nucleus, it's not going to see the charge of the nucleus. It's going to be something, see a smaller charge or even zero, because the electrons are going to shield that, you know, or reduce that effective charge from the nucleus. So this has some impact, the deviation from the model. So for large impact parameters, this is when the impact B is very large. So the alpha particle is moving away from the nucleus. So you can imagine, okay, now electrons, they will have a role to reduce the potential that the alpha particle is going to see. It's not going to be a pure Coulomb potential. Okay. So in this case, for large impact parameters, then there is a modified potential. Okay, the Thomas Fermi potential, where it's similar to the Coulomb potential. Remember, the Coulomb potential is just 1 over r, but you know they have this exponential factor here, where this is a constant defined by this, and so on. Okay, so maybe for large potential, because the Rutherford scattering, I did not derive actually the cross section. But the cross section is given by d alpha n over 4, the differential cross section. The differential cross section, 1 over sine to the power 4 theta over 2. The problem is that with that, the formula, it explodes at small angles. So the potential looks like this. It's in the book, if I'm not mistaken. So the differential cross section so it's per solid angle. Now, if you have problem with what's the solid angle, we can talk more about this. I think this is given by the sorry, this is the cross section. So this is the cross section. Okay, this is, if I'm not mistaken, this is given by d alpha over n over 4. I think this is squared because its cross section has an units of area, and then we have 1 over sine the power theta over 2, and this is to the power 4. So this, it will explode. When theta equals to 0, sine of 0 is 0. So this, the cross-section goes to infinity. In reality, we don't have something that goes to infinity. But this is based on just the pure Coulomb treatment of the problem. So when theta is small, you remember the impact is large. Impact parameter is large. B is far away. So the potential that one should use is not the pure Coulomb potential, but a modified potential. And when one can do the math and determine, the cross sections here. Also, deviation from the model for small impact parameters. So we have a problem when we have a large impact parameter, and we have a problem when we have a small impact parameter. We got deviations because the nucleus actually has a size. Okay, it's not like a point. It's not like a point with a positive charge, but it does have a size. And in that case, the potential is going to be different as we come closer. It's not going to be explained by the Coulomb potential only. Okay, but some other, well, it's a Coulomb, but not for a point source. So there are attempts. This is basically shows how this is the potential of the Coulomb, okay, from 0 to infinity. But in reality, since the nucleus has some size, finite size, then the potential is not going to go like this. But actually, as we go closer inside the nucleus, then the potential actually is going to be constant there. So anyway, I just wanted to talk about these deviations. This is the differential cross section of Rutherford. And this is basically the region at these scattering angles in radians, where it matches probably the experimental data, but at very large angles, or let me just put it in a different way. So if we plot this. Okay, so here we have theta, and then here we have phi. Okay, this is just going to, based on it's going to explode. Looks like something like this. Okay, in reality, this cross section actually like this. So in this part, in the middle, yes, we can use the Rutherford differential section to explain for different scattering angles. So here, this is scattering angle theta. Okay, but at very small angles this is because of the screening of the electrons. This is the real, it's a more real thing, because now the potential, we need to use a different potential, and also at very small impact, scattering angles, sorry, very small impact parameters. Also, there is a deviation between the experimental data and the Rutherford predicted cross section, and this is due to the finite size of the nucleus. So I'm going to stop here. I don't know if there are any questions. If you found this interesting, there is some nice physics in it. I did not try to put some math, but this example, I think it's something that here, this example, it's something now you can use always to calculate things. What's the probability of this happening, and so on. We have to think of these nuclei as targets. Okay, and all what we have to do is, okay, let's calculate a cross section for a specific interaction. Okay, let's calculate this area. So when we talk about, this is a differential cross section, but we're looking at a total cross section for a given interaction. So we're calculating for a target, and then the cross section. This is also, sometimes people are confused. They say cross sections are probabilities. The cross section is not a probability. It's an area. It has a unit, centimeter squared, or usually it's barns, I think, and so on. It's an area. It's not a probability. Although sometimes in textbooks they say, okay, probability, but it's not actually a probability. It's an area. But from it, we can calculate probabilities. Like in this example, where I'm showing we calculated what's the probability of scattering happening in this angle or greater than this, just by taking an area divided by a total area of the beam and so on. Okay.
Okay, Dr. Omid.
So since I've taken a lot of time because I gave a presentation at the beginning, but I hope everyone enjoys what we have been discussing. Definitely, there are a lot of I'm trying to give you just a tip of the iceberg, where he's now when you read such a book, you can start to understand the basic stuff, and then okay, now we can go for more advanced things and so on. So what I suggest, since now it's almost 2 hours, Dr. Ali wants to go to bed. Sure.
I'm here.
What I suggest is, okay, next week I'm going to talk about Bohr model, about Bohr. Okay, we're going to derive it a little bit, just show you the derivation, what it means, and so on, and the impact, how we can calculate, for example, the energy of characteristic X-rays and deviation from this Bohr model to a real atom. So what I'm going to do next time, 8 o'clock, when we start, we're going to open, this for questions on Rutherford, on what we have discussed so far. So if people are going to come late, they found, Rutherford is really boring and we don't want to hear it any longer. Okay, come at 8:30. Come at 8:30. If you want to hear some of the questions about Rutherford, be here at 8 o'clock. Or bring your question. I would suggest you bring your question, actually. Okay?
Okay, Dr.
Okay. So then I'm going to close the Zoom now. And hopefully we're going to meet, inshallah, next week. So the deal, 8 o'clock to 8:30, open for questions. 8:30 till 10, we're going to deal with the Bohr.
الساعة 8 بتوقيت مكة ولا القاهرة؟ لأن اليوم جيت متأخر، فاكر الساعة 8 بتوقيت القاهرة، جيت الساعة 9 بتوقيت مكة.
طيب لو قلت لك
مكة والقاهرة سيم تايم.
القاهرة ومكة نفس التوقيت، ايه رأيك؟
نفس التوقيت؟
ايوه.
أنا كان حساباتي غلط.
اوكي؟
خلاص إن شاء الله.
يلا طيب تصبحوا على خير. next week Saturday the same time. اوكي؟
إن شاء الله دكتور.
تمام دكتور.
يلا طيب.
شكرا جزيلا.
السلام.
شكرا دكتور أميد، إن شاء الله نشوفك الأسبوع الجاي.
وافتكر حتكون في اليوتيوب، يعني people can listen to it في اليوتيوب.
اوكي تمام.
و try to subscribe.
طيب حضرتك لو تقدر تشير
اللينك
اللينك بتاع اليوتيوب.
اوكي هو موجود، المفروض انه انا عامل. طيب اوكي I'm gonna share it, don't worry.
اوكي.
يلا.